Now, if you're not feeling very comfortable with chemistry and dealing with bond types and polar versus nonpolar covalence and hydrogen bonds, this is a really good time to stop the video and go back and rewatch 2.1 again and read your textbook, because I'm going to assume that you understand and can identify and apply these bonds from this point forward, because we're going to start dealing with water. So what is the molecular formula for water? Well, I think pretty much everyone at this point knows that water is also known as H2O. What does this mean? Well, quite simply that there are 2 hydrogens and 1 oxygen. Now, what type of bond connects these? Well, many of you probably know that this is a covalent bond, and you can identify that because this is going to be drawn as a straight, solid line. That's how you know that it's covalent. But in this class, it's never enough to just write covalent. You have to identify the type of covalent bond. Well, oxygen is going to be highly electronegative. Hydrogens are going to be weakly electronegative. And so the difference, the fact that one's high and one's low, tells us that this is going to be a polar covalent bond. Now, polar covalent bonds and nonpolar covalent bonds are both straight lines, solid lines. They look the same. So how do we tell the difference? Well, quite simply, if you have an unequal sharing of electrons, which is what polar covalent means, you have differences in charges. So this oxygen here is actually going to generate a partial negative potential, and the hydrogen here is going to be partial positive. The oxygen is partially negative because it wants the electrons, right? It's highly electronegative. Electrons are negative, and so therefore it becomes partially negative. Now, when you go through and you draw water molecules never exist entirely by themselves. When you think about a glass of water, a cell filled with water, doesn't matter. All of those are existing in a solution, an aqueous solution, with lots of water molecules around. So we have to think about these interactions of one water molecule to another. Now remember that this is always going to be in the context of these partial charges. So when you think about positives and negatives, what does that make you think about? Maybe something like a magnet? Well, what do magnets do? They attract to each other. When we have this attraction, what do we call that? Hydrogen bond. And how do we draw hydrogen bonds? Yes, this is a dotted line. So we start getting interactions, these hydrogen bonding interactions, which are the result of these partial positive and negative charges. And we're going to be drawing these by recognizing that this is a weaker interaction and representing it with dotted lines. So when we think about living things, we think about these solutions, we think about the fact we're big sacks of water. This is the context in which all living things are existing. Now, I understand that my drawings are not beautiful and perfect. That's the hazard of drawing on a laptop. But here's a beautiful picture of this in which you can see partial negatives. You can see partial positives. You can understand that this dotted line is a hydrogen bond. Solid lines are going to be covalent bonds. These partials tell us it's a polar covalent bond. And these interactions are what are governing this molecule of water.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge. even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
So let's take a look at some of these unusual properties. This is a challenging component for many students in the course, but it's a critical one. You need to understand how water and the hydrogen bonding properties of water allow living things to exist. And that's what these 4 properties really describe. So we're going to go through them one at a time, and we're going to connect each one to the property of hydrogen bonding. And we're going to do so by testing you in Socrative along the way. So make sure you have it ready. When we talk about hydrogen bonding, it's important to consider who the hydrogen bonding is with. Cohesion is the attraction between water molecules. Co is going to be a prefix that means between. And so cohesion is when one water molecule hydrogen bonds to another. It's between water molecules. This cohesion is what keeps water together. But adhesion is when the water molecule hydrogen bonds to its environment. And this is important because water will also want to stick to the things around it. Let's take a look, for example, at capillary action. Maybe you guys learned about this in Bio 1, or this is something that you've experienced in high school. Capillary action is the idea that if you take a very thin tube and touch it to a droplet of water, it will get sucked up that tube. Capillary action is what's responsible for bringing water from the roots of a tree all the way up 100 feet or more to the leaves at the top of the tree. What happens is the water that's up in these leaves and these surfaces is going to be used or evaporate away. When it does so, there's going to be cohesive forces that are pulling the water molecules along behind it up the force of that tree. There's also adhesion, and adhesion allows the water molecules to stick to the side so that you can actually get an interaction that doesn't just whoosh, fall out through the force of gravity. All right, so now I want you to test yourselves. Get out your Socrative and tell me, the formation of water droplets on your newly waxed car is mostly the result of what? If you need more time for any of these questions, always just pause the video and take your time to think about it. But the answer here is cohesion. The fact that your car's surface is coated in wax, a hydrophobic substance, which we're going to be talking about more over the course of this semester, is going to be something that it limits this process of adhesion. You don't get interaction between the water molecule and the environment because the environment simply isn't willing to interact with the water molecule. So cohesion forms droplets. Now, the formation of droplets on these pine needles is primarily the result of what? Good, this is cohesion and adhesion equally. You don't get droplets without cohesion, water, hydrogen bonding to other water, but you don't stay on the surface of that pine needle unless there's adhesion, which is the interaction, the hydrogen bonding between the water and the droplet and its environment, which in this case is the needle. Now, the formation of a meniscus, which you've probably seen in chemistry and are familiar with when you have to measure your solutions, it's the water seeming to climb the sides of this cylinder, is mostly due to which property? This is an example of adhesion. Now, just to be very clear, I would not ask you a question like this on the exam because there is clearly cohesion here in this process. but this is the best example I can give you where adhesion becomes a force that's creating something you can see. Whenever you talk about who water is hydrogen bonding with, make sure you talk about cohesion and adhesion. It's okay if you say that one force predominates, but when I talk about, or when I ask you about these properties of water, make sure that if you decide you want to talk about who the water is hydrogen bonding with, you need to consider both. Because the reality is that it's not a vacuum. If water is hydrogen bonding, which it is, it's going to be having both cohesive hydrogen bonds and adhesive hydrogen bonds. Sometimes there's just more of one than the other, or one's more important than the other in a particular scenario. Next, we can talk about the number and the stability of hydrogen bonds. And this is what you know as the different phases of water. When water is a liquid, it's going to be forming hydrogen bonds freely with other water molecules. And these are going to be dynamic. There's enough energy in that solution for the hydrogen bonds to both break and form, break and form, break and form, break and form, break and form. This is why you can dump a liquid component of water and it actually forms a new shape based on gravity and the forces that you're placing onto it. The hydrogen bonds that had it in one shape can break and form new ones, and yet it all stays together. Steam is when there's so much energy in the system that those hydrogen bonds are breaking faster than they're forming. There's very few hydrogen bonds that are being formed water to water. Ice, on the other hand, solid water, is when there's so little energy in the system that the hydrogen bonds themselves are both numerous and stable. They're sticking around. They're not being broken down. Now, there are many, many hydrogen bonds in a liquid form of water, even more in ice. And so it takes a lot of energy to be added into the system to break all the hydrogen bonds in ice and get it to water. It takes a lot of energy to get it from water into steam. This is known for chemists as high specific heat. There are so many hydrogen bonds in this water solution that it requires a lot of energy to break them all. Therefore, it requires a lot of energy to change the temperature, to raise the temperature of the water. That is why a watched pot of water never boils, because you have to sit there waiting forever for all that energy to get into the pot for it to finally boil, which, by the way, is water changing to steam. All right, so you know how this works. We're going to test you on Socrative. Here's the question. In which state are the hydrogen bonds most stable and thus most numerous? This is ice. By the way, this structure of hydrogen bonds in ice, which you're going to see in just a moment, is known as a crystal lattice. That lattice, think about your rose lattice that your grandmother has at her house, right? All those interlacing, forming wood pieces, right? And, you know, Rose Gardner over here. Yeah, all those different interactions, crisscrossing and forming a network, that's ice. Lots of numerous stable bonds, okay? Which temperature of water can absorb the most heat energy before evaporating? All right, now this is the duh question for you. Of course, ice can absorb the most heat energy before evaporating, but did you think about it? Or were you so worried about thinking about hydrogen bonds and energy that you got confused? Don't worry, I'm not trying to trick you. I'm trying to bring you back to the real world. Of course, you need to add more heat to ice to get it to boil than an already pot of liquid water. But what I want you to recognize is that this thing you already know is because of hydrogen bonding. You just never knew why. All right, now let's apply this to a scenario. Why does sweat, which is liquid water on your skin, cool you when it evaporates? Pause the video here, take your time. The answer is C. And the reason is because body heat breaks hydrogen bonds between the sweat molecules. So if you think about it, if you're taking the heat energy from your skin and you're using it to break the hydrogen bonds, well, it's no longer heat energy on your skin anymore. And so that loss of energy results in a loss of heat, which is a cooling effect on your skin. This is absolutely important for many different organisms. Your dog maybe doesn't sweat, but it has the same principle on its tongue, where it's evaporating moisture on its tongue, which allows it to cool its body. But let's talk about the fact that this is important not only for regulating body temperature, but hydrogen bonds also help to regulate Earth's temperature. So you can not only look at properties of water, which if you haven't realized it yet, and if you haven't read your textbook, you haven't yet connected the idea that this high specific heat of water is the reason why coastal towns, meaning like lovely places in California or the Jersey Shore, are usually cooler temperatures than inland. Well, let's connect this now to the idea that if you look at the hydrogen bonding properties of water, they allow organisms to survive even when things freeze. So if any of you guys have ever lived in the Midwest or an area that gets really cold, you've seen that when the lake freezes over the winter, there's a sheet of ice along the top. But if you go ice fishing, you can cut a hole in the lake and look down and you can go catch a live fish. Well, that's because ice floats. And if you're not sure of this, go get a glass of ice water and poke the ice. It's sitting there floating on the top. Ice, solid water, is less dense. But there are very few substances on Earth that are like that. Usually, if you're solid, you are more dense and you sink. But there are so many hydrogen bonds that are forming in that solid crystal structure known as a crystal lattice that it's actually forcing these water molecules farther apart, which means there's air that's being forced inside of that crystal lattice. And so that water is more dense than the crystal lattice, which is less dense. That crystal lattice is what you know as ice. So water has special properties: high cohesion, high surface tension, which is the result of cohesion, the ability to absorb large amounts of heat, and what kind of bond between water molecules is what gives it these special properties. Absolutely. Hydrogen bonds. Hydrogen bonds. Sink it in. Use that vocabulary word in any time, any answer you talk about water. Now I have one last property of water that I want to show you, and it's still about hydrogen bonds, but it's going to be a slightly different one. When we look at water, and when we think about water as this base substance of life, this is going to be a critical component for how we keep everything in your cell dissolved. Water is the ultimate solvent. It's an incredibly versatile solvent because it's capable of forming something known as hydration shells. Because the polarity of that polar covalent bond within the water molecule is very polar, because the partial positives and partial negatives are quite strong charges, they're capable of forming hydrogen bonds with a large number of substances. This ring that forms both around the partial negative here attracted to this cation and the partial positives here attracted around this anion, this is known as a hydration shell. A shell around the molecule formed of water, hence hydration. Molecules that are capable of forming and interacting with water, hydrogen bonding with water, are known as hydrophilic, water-loving. These guys are going to have hydration shells around them. Hydrophobic substances are going to be ones that are non-polar. They don't have partial charges. They're not capable of having this hydration shell around them. And so these are going to be water-hating or hydrophobic. All right, so there's going to be a couple of examples here that come up in just a moment, but let's think about this for just a second. Not a Socrative question, but why do we put down salt when there's snow and ice outside? Pause the video, write an answer, test yourself, see what you would do on an exam if I asked you this question. So what's the property of water that explains this? Use hydrogen bonds, put them in the correct context, and then use any other vocabulary word that's necessary. All right, so you wrote down an answer for your exam, right? Okay, so the first thing that I want you to do is check that you've described one of the properties of water. So you could have used any of our last 3 properties of water here. It's going to be all about the fact that you use the word hydrogen bond and that you did so in the proper context. So maybe you talked about the fact that there's a crystal lattice that forms, that ice and snow is solid water in which there's a crystal lattice with a large number of hydrogen bonds. Now I've used hydrogen bonds and in the proper context, and I've used my vocabulary word. Maybe you've decided to talk about the versatility of solvent, because salt is going to be dissociated. It's an ionic bond. It's going to be dissociated into an ionic and cationic and an anionic compound, and that hydration shells will form around these charged substances because hydrogen bonding is possible between the water and the ion. Well, what happens when you get this hydrogen bonding between the water and the ions? Well, now you are not hydrogen bonding water to water. The cohesive hydrogen bonds start to break down because they're being replaced with the hydrogen bonds of this hydration shell. Well, when you no longer have hydration bond or hydrogen bonds that are being formed between the water molecules, between this crystal lattice, that breakdown of that crystal lattice structure is what causes that shift into water. And now we go from ice into water. So we've lowered that melting temperature. And so this is a fantastic example of where you see this all the time, every day in the winter, but you maybe didn't think about why that salt is responsible for breaking those hydrogen bonds. Okay, so I want you to get onto Socrative, and I'm going to show you some examples of molecules, and I'm going to ask you, not if they're good substitutes for salt, but if, for example, this molecule on Socrative, tell me in Socrative, could this molecule be used as a substitute for salt? Pause the video and come back after you answer the next 2 questions. All right, so carbon to hydrogen, what kind of bond is that? Non-polar covalent. And carbon to carbon, non-polar covalent. And carbon to hydrogen, non-polar covalent. And carbon to carbon, non-polar covalent. All of these are weakly electronegative and equally weakly electronegative. So there's an equal sharing of electrons here. Non-polar covalent bonds do not receive partial charges. They do not have this unequal electron sharing. So there's going to be no part of this molecule capable of hydrogen bonding with water. If this molecule can't hydrogen bond with water, it can't disrupt that crystal lattice. It can't break any of those hydrogen bonds. It's not capable of adhesive hydrogen bonding. And so no, this is not a substitute for salt. Here on the other hand, oxygen to hydrogen, polar covalent. Carbon to oxygen, polar covalent. Oxygen to carbon, these are all polar covalent bonds. Now, I'm not saying that this is as good as salt, but hey, this could be used as a substitute for salt. It would, in fact, lower the melting temperature. Now, I have one last thing that I want to introduce you to really quickly, and that's primarily because we're going to be seeing water as a molecule, as something that we're going to be interacting with when we're building other molecules inside of the cell. Now, solutions that are composed of or are dissolved in water are known as aqueous solutions. So you may see this in your travels throughout this class. And I want to show you that water is not as stable as you think. Water is actually pretty dynamic. in part because of the fact that there is this hydrogen bond that's forming between two water molecules, this cohesive hydrogen bond. And on rare occasions, that hydrogen bond results in a hydrogen jumping ship, joining another molecule and forming what's known as hydronium, H3O+. But since this exists in a background of water all the time, we just subtract the H2O, and this becomes that thing that you know as H+. So every once in a while, this water dissociates, it breaks apart into a hydronium or hydrogen ion and hydroxide. That hydronium ion, that H+, being in abundance in a solution, is going to be known as acidic. That basic solution, an abundance of hydroxide, is known as basic. And next class, we're going to take a look at some different functional groups that can be contained in larger organic molecules and how they're capable of interacting with water and forming both acidic and basic solutions. All right, guys, please make sure that you take the time to practice describing what's going on in water solutions. It's important that you can describe any and all of these different properties of water, and make sure that when you are doing so, not only do you use the word hydrogen bond, but in a correct context, and you follow it up with appropriate vocabulary to demonstrate to me that you understand that component as well as being able to look at molecules and describe their chemistry to me so that we can think about them in larger aqueous solutions. You have a recitation, which is a packet of practice problems that will be opening up tomorrow, and then that will be due and we'll begin our next lecture on Wednesday.